Hi, my name is Stephen Tansey, and this is me. Today, I'm going to be talking to a couple people in the hopes of finding where ratios and proportions play into everyday life. I'm hoping this video provides some examples so you can see that math is more than just what you learn in the classroom. It really is something that you'll see everywhere in life. Up first, we'll be talking to Austin Crossley, and I'll let him explain more about how ratios and proportions come into play with his major.
It has a lot to do with physics due to the fact that you have to be able to calculate very particular measurements on either the atomic scale or a mass scale, like a building. So to be able to have those calculations is useful, especially when you're trying to look at how smaller particles behave. Being able to scale that into other equations to be able to find ways to harvest energy or find ways to invent things that are going to work a little bit better than what we had before. So it's definitely pretty useful for those kind of things. A lot of times with electrical engineering, if you have improper resistors or capacitors, things like that, you got the ratio wrong somewhere. It definitely could end up in explosions, which is always fun to see. But ultimately, it's a matter of scaling your answers correctly. So a lot of times, what people do is they forget to move a decimal place over, or they forget that something's 10 to the power of something. So then they'll have a scaling problem there, just because they'll be using something that is scaled to a different measuring unit. And they're putting it into their equation using another separate unit. So that can definitely make an effect. I really enjoy woodworking, and one of my favorite things was seeing, some people accidentally get the measurements wrong or the proportions wrong. And so they would be trying to create a box and they would end up making some kind of catastrophe. Just definitely not what they were originally intending on, making. It just kind of looks wrong because they've either gotten the sides too long and the top not long enough, and it's got holes or things like that. So that was a lot of fun to see. The calculations that we do in physics classes in Plattsburgh are pretty small. We're not really measuring the distance the Earth to the moon. So we don't really have those super big numbers that we have to deal with. So normally we're just kind of calculating things the sun shining into a room, the rays going down and reflecting off of certain substances. We would have to be able to get the proportion right because one of the major laws of energy conservation is that energy is not created or destroyed. So if you suddenly had an equation where all of a sudden you had 9 newtons and you ended up with 8.5 newtons at the end, something's going on. Either that energy is elsewhere or something's going on with your proportions. But for the stuff that we do just in general physics early on, you don't really see too much of it. But it definitely can apply when you're starting to look into different solar systems, different planets, trying to scale those up.
So ratios can also be applied to everyday things like basketball here. So with basketball, you have to make sure that you have a proper proportion from the size of the rim to the actual size of the ball. If you have too small of a rim, you're going to start getting that carnival ride situation where you toss the ball in and it never goes in because it's too small. So to be able to have a fair game, you have to be able to make sure that your rim is bigger than your ball. There are different kind of ways to measure that. Different rim sizes go for different games. Not necessarily basketball, but laundry basketball or something along those lines. But as long as your ball is smaller than the rim.
The next person I went to see was my friend Nathaniel McCauley. He is studying as a chemistry student, and he was going to give me some more insights about how ratios and proportions plays into the field he's studying.
Ratios right now are probably the biggest part of chemistry, and it's one of the first things you learn going into it. And in the very basics, it will cover a components of a compound that you're making or a reaction that you're working with. Very basically, you can get a simple equation like this when you first start chemistry, And you'll notice that you have these big numbers right in the front. And what that's basically saying is that for every one molecule of this, you'll have 2 of this. And that is the fundamentals of chemistry. And that's one of the most basic ratios you work with across the entire 4 or 8 years you do of chemistry. Looking into the future, as an organic chemist, I'll be working with a lot of percentage ratios with compounds I make. So in a lab, I'll have to synthesize something, let's say like aspirin, which is a compound most commonly used for pain relief. And in the lab, some of those compounds can form variations of themselves. So what they call, I believe they call diastomers or enantiomers, which is basically just a isomer of itself. It's how it can change its structure. It's the same compound, the same mass, but it could have varying properties. And so in lab, I synthesize that and I make the wrong structure. Aspirin especially, it can be quite toxic to somebody. So if you're making this compound, you're synthesizing this compound, you want the highest possible yield, the closest number to 100. So you can get something like 99.8 is probably the highest you'll ever get. That will be the amount that you want. So you have the 99.8 that you want, and then the 0.2 that is the remaining, that's what you don't want, which can be easily just taken out of the system. So carbon itself is a very basic compound. You don't have it here. It can form, in a term, allotropes of itself. That's the most basic term for it, where it can bond with itself in a certain way. So there are a couple different ones you would know. So graphite or graphene, which you'll find in kind of pencils and that sort. And that's like a soft, hard carbon. Or you can get, I think it's called Buxton balls, which is what they have in tennis rackets, and it's just a carbon structure. And all that varies between those different structures is the ratio of carbon you have per area. Okay, so this is, again, one of the most basic things you'll see in chemistry. And what this basically is stating is that C is the element carbon. And these 2 numbers, you'll see, one is related to its atomic mass, which is how much that compound weighs in a relative aspect. And the 6 will be the atomic number. So if you're looking at a periodic table, the 6th element along will be carbon. Now it's done in such a way that when you look at its protons, electrons, and neutrons, which is what is the fundamentals of chemistry, these very tiny particles, is what makes up the compound itself. So the atomic number will always relate to the number of protons and electrons you have. And with dealing with ratios, protons and electrons are always 1-to-1. And in their base forms, they're always 1-to-1. However, neutrons can vary. So in the example of carbon, you have 6 protons and electrons, and to find the number of neutrons, you'd have to subtract the atomic mass from the atomic number, which again will provide you with 6. So if you look at the ratio between protons, electrons, and neutrons, it's typically a 1-to-1 scenario, or a 6-to-6-to-6. And so yeah, I guess that's a big thing. So if you're working with pool water, you're gonna go swimming, and you always hear the term is chlorinated. What that means is that at some point they'll put a couple of these tiny little compounds, which are effectively, in simple terms, chlorine. And what it will do is it will go into the solution in the water, so it will mix with the water, and it will help keep the water clean. So again, if you have a compound that's what they use is concentrated, if it's too strong, and you have too much chlorine in the pool, it could actually cause your skin to dry out really quickly. It can cause your skin to be agitated and turn red, and that's what actually causes your eyes to turn red. So if you go underwater and open your eyes turn a little red because the chlorine agitates it. So if you had too much, it could do a bit more damage to your eye. So that, in essence, is a huge role of ratios. So the chemist who comes up with that compound has to make sure it's in a right approximation with one another, right ratio. If it's too little, it won't do its intended job. So you have the two varying aspects. If you go too much, it can be harmful, and if you get the ratio and it's not, if it's too small, then it doesn't have any effect at all.
My next interview brought me all the way down to Albany, New York, to talk with my friend Tanner Kuhn. Tanner is a filmmaker who lives in Albany, and he's going to be talking to us how ratios and proportions come into play even in film.
My name is Tanner Kuhn, and I am a professional videographer for the state of New York, and I also freelance as well. In my line of work, like ratios, specifically, when you're creating a video, you generally make one by 16 by 9, which is what most screens are nowadays, is 16 by 9. That's the ratio that you use, and the old one used to be 4 by 3, which is like basically a box, like an old CRTV would be that. And like the TVs that we had in my high school were 4 by 3, and now TVs like my computer monitor is 16 by 9. So I need to make videos in 16 by 9, generally speaking, although there are news organizations that do ask me at the state to export things into 4 by 3 so that they can actually use them, because their software or their whatever they use to get their broadcast out is not 16 by 9, it's 4 by 3. So if somebody gets that ratio wrong, like 4 by 3 or 16 by 9, then your video, okay, so I'll do 16 by 9 first. So if you want a video in 16 by 9 and you export it into 4 by 3, it's going to look like smushed and it's going to look squarish instead of a rectangle shape. Now, if you were doing it the other way and you did 4 by 9 and you wanted 4 by 9 but you got 16 by 3, obviously it would be a rectangle instead of a square. Now, if I sent a news organization a video in 16 by 9 and they wanted 4 by 3, it's going to stretch out the image and crop it in a weird way, and it won't look good at all. So it needs to be the right ratio for them to use it. Yeah, I guess movies, that's something everyone understands. Movies are all 16 by 9 now. If you saw a 4 by 3 movie, it would be like a square, and most of the screen would be black, and you'd be like, "What? Why is it tiny?" You'd be so confused if you saw a 16 by 9 or a 4 by 3 movie instead of 16 by 9. Well, other than resolutions, I suppose the rule of thirds is one. So, in order to make a pleasing image, it needs to follow a rule called the rule of thirds, and that means that you divide the shot or your frame that you're getting in your camera into a grid, which is a 3 by 3 grid, and you either center something on the two vertical lines or horizontal lines. So if you're taking a picture of the horizon, you want the horizon to be on one of these two lines and not in the middle, because the middle just looks weird and it doesn't follow the rule of thirds. It's more a picture's more pleasing if it follows that. So you put the horizon up here, you get more of the ground, or if you put it on the lower line, you would get more of the sky. So it depends what you're going for, but you generally want to follow that rule. Because if you don't, it's not going to look as pleasing as it could have been.
And last but not least, I drove over to my hometown of Red Hook, New York, to interview my friend Mike Gabraszewski, who is a personal trainer.
My name is Michael Gabraszewski. I work at IXL Health and Fitness as a personal fitness trainer. Ratios and proportions come into my line of work a ton, both for programming, for weights, exercises, cardio, everything like that. Also to go with people's meal plans and nutritions. Also, people's bodies are made up of a ton of different proportions, and you can use those to determine how healthy they are, and you can use that to track all their progress and everything like that. So when you first start training someone, which you'll sometimes do depending on what their goal is, especially if their goal is for strength training, what you'll do is you'll take kind of like a baseline max test of how strong they are. And what you'll do from there, so that'll be like 100% of what they can do, but you can only do that once. So what you'll do is use ratios and proportions and percentages to kind of break that down. Into the program, you might use like 85% at like 10 reps or 6 reps, rather than going at 100% all the time. So it kind of helps you build the most effective workout plan to get your clients where they need to go. Sometimes if you make a mistake with your ratios or proportions, what will happen is you'll either make somebody go a little too heavy, so that runs a risk of injury if you're a little bit off there. Otherwise, you might not get the most effective workout program because you might not be challenging someone quite enough. Also, if you get ratios and proportions off when you're doing kind of nutrition and meal planning and things like that, again, if you're off by calories, you're off the protein, carb, and fat balance, again, you won't get the most effective workout program and nutrition program for them. Another way proportions come in is just people's bodies. So if somebody comes in for bodybuilding or posture, things like that, most people are dominant on one part of their body, and so that will actually make different proportions in one side to the other. And so what you can do is you really want to make sure you get the body nice and symmetrical so the muscle balances are all there.